Hello and welcome to the Sheldrake-Vernon Dialogues with myself, Mark Vernon, and Rupert Sheldrake. Hi there, Rupert.
Hello, Mark.
Rupert, today we thought that we could talk about field theory. This is really at the heart of modern physics. I was reading a little bit before we were speaking just now, and Einstein apparently made this comment that there was physics before Maxwell, who was the great pioneer of modern field theory along with Faraday, and then there was physics afterwards. So it just goes to show how important fields are for electromagnetic fields, for quantum fields. Einstein's space-time too is a kind of field theory. And so it's really fundamental to modern physics. And I know it's something that you've thought a huge amount about as well, because of your own proposals. Take us away with fields. Why does this interest you?
Fields take us beyond the narrow views of nature in 17th and 18th century science, which were mechanistic, mechanical, about pushing and pulling, contact, and so forth. The one big mystery in classical science was gravitation, because Newton's theory of gravitation showed that every particle of matter attracts every other particle of matter in the universe, that everything's interconnected, but he hadn't a clue how that could happen. And the real revolution, I think, begins in the 1840s with Michael Faraday, who realized that when electrical charged surfaces influence other ones, you have electrostatic fields. There's an influence between them, which he called a field, because it seems to be a continuous influence between the positive and the negative charge. And with magnets, then the way that north poles of a magnet attract south poles of another magnet, or repel the same poles repel at a distance. He again explained in terms of fields. Now, why he was interested in fields was because they suggested there was some continuous influence moving through space that wasn't matter. Matter was stuff, and everyone agreed about matter being stuff. Everyone agreed about energy, about movement, for example, moving billiard balls. But fields were something new to science, the idea there's something invisible acting at a distance through spreading out from a magnet or an electrically charged body. And for him, the key point about this was that it was not an instantaneous action at a distance, but took time to propagate. And the fields had curves within them. So he thought that they were actually spatial patterns, invisible spatial patterns. And furthermore, he thought that electrical and magnetic fields were moderated by what he calls lines of force. When you look at those iron filings around a magnet, you see all those lines going around the magnet. In modern textbooks, it's treated as if lines of force are somehow imaginary. But for Faraday, there were physical lines through which there was a flow. Out of one end of the magnet, the field flows round and comes in the other end. It's closed loops going through lines of force. Well, when Maxwell wrote his equations and showed that light is an electromagnetic phenomenon, this was an amazing unification of electricity, magnetism, and light, which has transformed all the sciences, and most of our technologies rely on them today. I mean, we're talking over a computer link. People are seeing this on a screen, hearing it from a device. All of this depends on electromagnetism. Mobile phones depend on radio waves, so does radio and television. So these have had a transformative effect on science and technology, but also on our thinking about nature. Because Einstein then generalized the field concept to gravitation, and thought of the whole universe as linked together within the universal gravitational field. But gravitational fields are very different from electromagnetic fields. They only attract, they don't repel, and you can't block them or screen them. And every particle of matter is influenced by the gravitational field and in turn influences it. The speed at which gravity propagates we've already discussed, and it's probably very, very much faster than the speed of light. And some people, including Faraday, considered the possibility that it was instantaneous, an instantaneous action at a distance. And in fact, from the point of view of the calculations of physicists about the movements of stars and planets, it's taken to be instantaneous. No one knows the speed, it's probably very high, but effectively it's treated as instantaneous. Well, then the next fields to appear on the scene were the quantum matter fields, when de Broglie in the 1920s showed that material particles like electrons were vibratory patterns like light. They were vibratory waves. Then they had to be waves in something, and so the idea was that they're waves in matter fields. An electron is a wave in an electron field, a vibratory pattern of energy. A proton is a wave in a proton field, a series of waves. They're processes, wave processes within fields. Then, in terms of understanding the atomic nucleus in more detail, more fields came into the picture. The strong interaction, or strong nuclear force, or the strong nuclear field, holds three quarks together to make them into a proton or a neutron. And the weak interaction holds atoms, holds the nuclei of atoms together, and is involved in radioactive decay. So we've got very localized fields. These strong and weak nuclear fields are confined to atomic nuclei. They're very, very local, as the exact opposite of gravitational fields, which are universal, and electromagnetic fields, which can spread out indefinitely. So in addition to all these kinds of fields, I think there's another kind as well, which I call morphic fields, which are fields of form, fields which shape the form of plant petals, flower petals, plants' leaves, embryonic structures as they develop, animal embryos, that are basically formative fields that underlie biological and chemical morphogenesis, underlying the forms of molecules and of crystals, as well as animals, plants, and microbes. I think morphic fields also shape planetary systems and galactic systems, together with gravitational and electromagnetic fields. And I think morphic fields work by influencing probabilities, bringing about patterns in otherwise random events. I also think they have a kind of memory given by what I call morphic resonance. So here's a range of very different kinds of fields, and one of the projects in physics has been to try and unify them, to see them as all aspects of one fundamental field. That's one of the ambitions of superstring theory, which has 10 dimensions, or M theory that has 11, trying to see the known fields of physics in terms of some primal field that was present at the moment of the Big Bang and has split up to give these different kinds of fields. But these attempts to unify the fields have only met with limited success. The electromagnetic field and the weak nuclear field can be unified theoretically, but somehow the quantum fields and quantum physics is famously not really unified with gravitation or gravitational fields. So there's still an outstanding problem at the heart of physics. And all these unification attempts ignore morphic fields, the fields of form, throughout nature. So field theory is still very much an unfinished business, even though it's so important for the whole of modern science.
One of the things which struck me as you were talking there is how with fields come various principles that are then thought to guide the investigation of nature. So one you mentioned there at the end is the unification of the fields, which presupposes a unity within nature. And as is well known, both Faraday and Maxwell were religious people. And for them, that intuition sprang from the sense of the unity of creation within God. God was one, and in some way, creation therefore reflected that. Another principle that is implicit in what you're saying there is the principle of analogy, that by looking at how things work in one part of nature, you can make inferences, which of course then need to be tested and so on, but you can make inference about possibilities in another part of nature. So I believe that Faraday was struck by how in a fluid there's waves and so on, and the transmission of energy. And so similarly across a field, there was an analogy with fluids that could be made. And then this was very productive in terms of developing the theory. So this idea of both the unity of all things and then also the principle of analogy, I guess that is very powerful, for example, with your extension of field theory into morphic fields.
Yes, morphic fields are an attempt to understand form in nature, which is basically not understood very well in terms of existing physics. In the 17th century, there was an attempt to reduce scientific explanation to what Aristotle had called material and efficient causes, matter and forces, and energy is what we'd now call energy, moving causes. Previously, the medieval view and the Greek view under Aristotle's influence had been that to explain things you need to have the matter of which it's made, the material cause, the energy that makes things change, but you also need the form that gives shape or pattern to things, and the goal or purpose, the end to which things move. And he thought things fall to earth because the proper place for heavy bodies is at the earth. They were drawn towards the earth, attracted to the earth, because that was their end or goal. The field was acting, the gravitation was acting as a final cause. I think it's very interesting when you think about it, and one of the things I'm thinking about a lot at the moment is the causal role that fields play, because they're not really moving causes. A field is not a moving cause like a billiard ball is, or with kinetic energy. A field can be just sitting there. A gravitation, the Earth doesn't have a gravitational field because it's in orbit, because of its movement. It has it just because it's made of matter. And so it's not a material cause, because gravity is not made of matter. The gravitational field extends far beyond the Earth and influences other matter. It's related to matter. It's not made of matter. It's not made of movement. So in terms of the old analysis of causes, fields are much more like formal and final causes, which the sciences tried to abolish in the 17th century. And so they have formative effects. The gravitational field has a formative effect. That's why the sun and the moon are round, and why the Earth's more or less round. The gravitation actually has a formative effect, and it has acts as a final cause, pulling things, working by attraction or repulsion. It's only attraction. What's interesting about the magnetic and electric fields is that they're completely polar in every sense. There's a polarity between electricity and magnetism. A flowing electric current generates a magnetic field around it. There's a polarity within electricity, the positive and negative poles of a battery, for example, or positive and negative poles in a plug or in any electric circuit. There's also a polarity in magnetism, the north and the south. So everything about it is polar. And according to Maxwell's equations, there's even a polarity in electromagnetic radiation in time, because according to those equations, light can flow from the future towards the past, or from the past towards the future. These are called the advanced and the retarded waves, respectively. So there's every kind of polarity. And it's interesting that polarities are not completely equivalent. You might think that a magnet, because it has a north and a south pole, and north poles repel and north and south poles attract, opposite poles attract same poles repel. It might sound as if attraction and repulsion are completely equivalent, but they're not. And actually, I've been playing with magnets a lot recently. I made a little film which I think illustrates this point. What this little film shows is that if you take some small bar magnets and you just throw them down at random on a plate, the poles, the similar poles will repel each other, opposite poles will attract. But the net result is not a kind of stasis of attraction and repulsion just leading to a kind of muddle of everything mixed up together. What predominates is attraction. And so when magnetic poles, similar poles repel, the magnet twists around until the opposite poles attract, and then they come together and join together. So there's a kind of self-assembly happens under the influence of these fields, which this little film illustrates. And I think you've got it on your computer, and if you could show it now, we could look at that in action.
So it is fascinating because, as you were saying, it's not just the sense of attraction appealing over repulsion, but also there's an order there. As you say, it sort of self-organizes as well. Yeah.
Yes, well, I think this self-organizing ability, you see, is one of the things that fields do. That there's a seemingly equivalent attraction and repulsion, but what comes out of it is the whole thing turns into a big long bar magnet. Now, I've done this also with some little magnetic balls I have, and there where they roll around, you get things forming into loops, but they all self-organize. And a lot of things within living organisms self-organize, microtubules, crystals self-organize, all sorts of things self-organize, partly because they have electrical forces which have this field quality. Also, I think morphic fields underlie a kind of self-organization. So fields can act as formal causes. They cause form and pattern. And so they're not just about matter and energy. And if you think of gravitation, which we've already discussed, it doesn't lose any energy when it attracts things. The Earth doesn't lose energy when it attracts a meteorite. The amount of energy in the Earth remains the same in terms of its mass. In fact, the mass increases when the meteorite is attracted to it. When a magnet attracts something, it doesn't lose any energy. There's no loss of magnetic energy. So it has this formative ability, which is working in a different way from energetic causation, as I was saying, for what Aristotle called a formal cause or a formative cause. So I think fields provide an ingredient in nature which was missed out in 17th century science. And as Maxwell said in that quote you gave us, the introduction of field theory completely transformed science. So most of what science is explaining at the moment is explaining invisible influences. The electrical and magnetic fields are invisible. Electromagnetic waves are invisible. This room I'm in and the room you're in are filled with mobile phone transmissions, radio and TV waves, completely invisible. So the whole universe is filled with these invisible influences. I think that our minds also are field-like. They work through morphic fields, in my view. So when I look around me in the room I'm in now, and when I look at the screen with you on it, I'm seeing an extended world. My vision is extending into the world. The fields of my mind, I think, are coupled to the electromagnetic field of light. And just as the electromagnetic field is extended through the whole room, so my vision extends through the whole room when I direct my attention to different places. It's a kind of reverse field, the light coming in, the field of vision going out. But it's field-like. Minds are field-like. They're not particle-like. They're not like billiard balls. They're extended. We form extended concepts. We can recognize forms. We can experience things extended in space because of the field-like nature of minds. And I think it's particularly interesting that if you look at the history of the field concept, among the ancient Greeks, and particularly for Aristotle, what we now call fields, he called souls. Well, one of the very first sayings we have from pre-Socratic philosophy in ancient Greece, from the philosopher of Thales, Thales said the lodestone has a soul, or magnets have souls. The lodestone was a kind of magnet. And so the idea that there's a soul in the magnet, or beyond and around the magnet, an invisible influence, was then used by Gilbert in his 1600 book, De Magnete, where he showed that the Earth is a magnet. Compass needles point to the North Pole, not because they're pointing to the North Star. It's not pure astronomical north they're responding to. It's the Earth itself, the magnetic field of the Earth itself. The whole Earth is a kind of magnet. And the magnetic field of the Earth extends all around the Earth. But he didn't call it a field, he called it a soul. He called it the Earth's soul, the soul of the Earth. And in the ancient world, the Neoplatonists spoke about all the universe being held together by the soul of the universe, the anima mundi, which held the stars in their place and underlay the whole order of the cosmos. Well, that we now call the universal gravitational field. And Aristotle talked about the vegetative soul, which is the soul that shapes the growth of the body of plants and animals, which in biology is now called the morphogenetic field, the form-shaping field, plays much the same role as Aristotle's soul. So the idea that minds are field-like, that our perceptions and our activity, the activities of minds are field-like, connects with a much more ancient understanding where our modern science has replaced the old idea of souls with the idea of fields. But very much the same properties are inherent in them. Fields, like souls, are extended in space. They bring about ordering of nature. They have a formative influence. And they also attract things towards goals, just as a magnetic or a gravitational field attract things towards them.
So I want to put my sort of skeptical hat on a moment just to see how that develops the conversation. I mean, one thing that's not a skeptical response is that I think this idea that invisible entities are part of existence, that too goes back to the ancient world. I mean, the character who's sometimes mentioned here is an Anaximander, and he proposed that all things are what he called epeiron, which means from a kind of unbounded, unfixed origin, and then come into form from this epeiron. Sometimes it's translated as the infinite. But the point is that it sets a principle up of making a proposal that then is justified not because it's directly detected or seen, but because of its effects. And the effects therefore can be accounted for by the theory of that which is an entity underpinning all things. So, I mean, that feels like it's a very ancient principle that is still very operative in modern science as well. But I suppose that modern science, though, too, does have this reductive imperative. And so aligning modern field theory with ancient notions of soul doesn't modern theory try to remove some of what would have been part of the ancient notion of soul? I mean, for example, you mentioned Gilbert there, and if I remember right, it was actually quite disturbing for people when Gilbert suggested that the Earth was a soul, uncoupled from the heavenly soul. If the magnet wasn't drawn to the North Star but was drawn to the North Pole, then that did suggest a kind of split away from the celestial, and the terrestrial domain could have an autonomy of its own. And so you get a kind of implicit reduction there. So I wonder how you feel about the modern notion of field, the ancient notion of soul, and actually a kind of reduction or loss. It is a sort of metaphysical shrinking. It's you might say it's seeking for immanent explanations rather than transcendent explanations, or explanations which are accounted for within the natural sciences, not needing some kind of spirit or theological insight to fill them out.
The idea of the Earth having a soul being limited doesn't seem to me to raise any new problem, because Thales and the ancient Greeks already thought of the lodestone or the compass needle. It was a naturally occurring compass, as having a soul that was localized within and around it. And so it wasn't as if it had to be universal. What was universal was the anima mundi, the soul of the whole universe that held everything together. And we still have that with the universal gravitational field. So I think these explanatory principles, invisible though they are, you could say that they're just explanatory principles, that no one's ever seen a gravitational field. We only know it through its effects. And there are still rival theories of gravitation to Einstein. So Alfred North Whitehead had a different theory of gravitation from Einstein, a different theory of relativity. But Faraday's point was these are not just heuristic devices, they're real. And so when you see the lines of force with magnets, with iron filings around a magnet, some of his contemporaries said, well, those lines of force are just produced by the way the iron filings interact with the magnetic field. They're not actual lines really there. And Faraday was convinced there were. His last paper was on the physical nature of lines of force. And he explained many magnetic phenomena. The intensity of the magnetic field is the number of lines of course that a wire passing through them will cut, the amount of electricity that's induced in the wire passing through the lines of force. Well, this is still used in physics textbooks today. They still use this concept of the lines of force. And then at the end of the explanation, that totally depends on lines of force, they say, however, of course, the lines of force are imaginary. And they just sort of take away the entire rug on which the whole structure of explanation has rested. So there's a great ambiguity in modern science about the reality of these lines of force. And I think the nature of the fields is obscured by the haze of equations which shield them from view and from thought, where Faraday's genius really was to think of them as real and to think of them as things you could experiment with. Whereas now, physics textbooks go straight into sort of equations for fields and calculations about field strength and particular points in the field and so forth. And so thinking about what the field actually is becomes rather difficult, because you feel you've got to wade through vast amounts of mathematics in order to get there. And when I talk to some of my metaphysically educated friends, like Alex Gomez-Marin, for example, who has a PhD in theoretical physics, ask him to sort of look through all those equations to what the field actually is. He's rather at a loss, because that's not what you're taught. You're not taught what they are. You're taught how to calculate various aspects of them. So that's why I think that the whole concept of fields is so fascinating, because it is used to explain so much of nature, and yet we have so little idea as to what they actually are, and indeed to how they very little idea about how they relate to consciousness, because consciousness is field-like. Souls, in the old view, related to minds. The psychology really literally means the psychology of the soul, the psyche. We now think of it as the science of the mind. But there's a relation between minds and fields which is nowhere discussed within physics, because it assumes that all fields and all nature is unconscious, creating the hard problem of consciousness, because somehow you've got to get consciousness back in there. There are those who argue in the electromagnetic field theories of consciousness that consciousness is actually created by some electromagnetic fields and their activity in the brain, that it's nothing but the electromagnetic field experienced from within. I myself think that consciousness is related to morphic fields, which are in turn coupled to or connected with electromagnetic fields. But there's something about fields theory that's still radically incomplete. And that's why I personally spend quite a bit of time thinking about it, and why I've recently been rereading Faraday, because Faraday, who was the first person to articulate the concept, was grappling with it at a quite profound level. As you mentioned earlier, like Maxwell, he saw this in terms of a much larger picture. He saw fields as fields of force, and he thought matter itself was produced by fields, or fields of force. He thought particles of matter were not particles of actual stuff, but were actually produced by forces which were in fields. And in a sense, Einstein confirmed that aspect of Faraday's thought, because for Einstein, fields are not produced by matter. Rather, matter is produced by fields. A material particle like an electron or a proton is a vibratory pattern within a field, combinations of fields and energy. So fields and energy are now the most fundamental principles in physics, and matter is produced by fields and energy. Which is why Karl Popper, the philosopher of science, said, through modern physics, materialism has transcended itself, because matter is no longer the fundamental explanatory principle. Rather, fields and energy are. Matter's explained itself in terms of fields and energy. But then, what exactly are fields? And we come to a fundamental principle. There's a wonderful lecture at the Royal Institution. It's online, given decades ago by Sir Lawrence Bragg, talking about magnetic fields. And he says magnetic fields are an ultimate explanatory principle. You can't say what explains the magnetic field. When you reach these fields, you've reached the ultimate level. And even if there's a unified field theory, even if there's a superstring or M theory managed to explain magnetic fields in terms of some primal superfield with 10 or 11 dimensions, it's still fields all the way down, and you don't get beyond that. They're ultimate explanatory principles, ultimate parts of nature, and their properties are to be extended in space to bring about forms, patterns, to influence processes within their region of influence. And that was one of the most fundamental definitions of a field for Faraday, and subsequently, a field is a region of influence. It's a region of space in which things are influenced by the field. And I think it's interesting to come back to the very first metaphor. When Faraday used the word field, he took the English word field, which we use to apply to agricultural fields, football fields, field of trade, field of view, field of interest. All these usages of the word field were already current. But the most primary one is field, an agricultural field. And what an agricultural field is an area from which woodland has been cleared. This is the primary formation of agricultural fields in Britain and in Europe and in most parts of the world. It comes about by clearing woodland. And you then have a cleared area, which is a region of activity in which you can sow crops and you can grow things or have pasture and raise animals and things. But if you don't do anything to the field, then brambles grow in, saplings establish themselves, and in most parts of Britain at least, the field turns back into woodland. I live next to Hampstead Heath, and there are no longer animals grazing the heath, unless it's mowed from time to time. The grassland reverts to woodland, and a lot of Hampstead Heath has reverted from grassland when it was grazed up until the 19th or early 20th century, has been taken over by woodland. So a field isn't just a passive area, it's a region of activity. And so I think that the very word field is a good word because it helps to connect this scientific idea through metaphors, through analogies, with something really quite concrete, namely agricultural fields.
And also that sense of activity relates back to, you mentioned earlier, Thales, who looked at the lodestone, but it also led him famously to make the remark, all things are full of gods, because of that active activity that's inherent in what we now call fields. And so maybe that's also a way of linking back this notion of field to soulfulness, to a kind of intelligence, a living wisdom that's part and parcel of fields. Maybe it acts in one very particular way that's quantifiable in terms of mathematics when it comes to electromagnetic fields. But if fields extend throughout the whole of nature, morphic fields being the case in point that we've mentioned as well, then that kind of habitual patterning, intelligence forming, wisdom shaping flow through nature connects us back in a way through to the ancient insight that all things are full of gods. Fields, if you like, can both help focus into a mathematical form, but also help expand into a dynamic sense of nature, which I know is part of morphic fields. Hey, look, that again is a subject that feels like, because of this heart of mystery in the middle of what science so frequently talks about, as we've already discussed in relation to energy and matter and gravity. This is a sort of expansive notion of thinking about modern science, which I really like, rather than closing things down. So thanks so much for that.
Well, thank you, Mark.